Okay, so, well, thank you for being here. So, yeah, so the idea is that I give you some, let's say, background and idea of what we are doing in the program on rough high-energy landscape. So I would like to start, so the rough energy landscape in high dimension is really the things on which we are working on. So high-dimensional rough landscape appear in many contexts. And this is why also if you look at the people that are here, there are some physicists, but also computer scientists and mathematicians. So I would like to start first giving you the different contexts in which there are rough energy landscape. And then I would like to go on telling you what are the common questions, actually, that we are asking, on which we are working on. And then I will give you one or two concrete examples. Okay, so let me start. So first, rough energy landscape has been something that has been discussed a lot in physics. I think for a long time, just like a metaphor, not something that is really useful to do computation. And then I think especially in the case of disorder system, there have been some real progress. So I would like to, there is one field or one physical problem in which thinking about energy landscape is, let's say, an important way to think about the problem, which is the case of the glass transition. So we'll start with this. So we start, let's say, with context and questions. And I will start first with the context in physics, and so with the problem of the glass transition. So first, what is the glass transition? So the glass transition, if you take more or less any kind of molecular liquid, and you cool it fast enough in order to avoid the crystallization transition, the liquid enters into a metastable phase, which is called supercooled. And in this supercooled metastable phase, if you decrease the temperature of very little, let's say 1/3 of the melting temperature, something which is small compared to the typical temperature scale, the relaxation time of the liquid increases very, very fast. It can increase of 14 or 15 order of magnitude. At a certain point, the liquid does not flow anymore, at least on, let's say, human or experimental time scale, and so we declare it an amorphous solid. And so what is interesting, the problem of the glass transition is understanding what is the physical mechanism that makes that the liquid relax so slowly. Is there some underlying collective phenomenon, some underlying phase transition that is responsible for this dramatic slowing down? And actually, the phenomenology that you find in glasses, so in molecular liquids that form glasses, you can find also in many other systems, like in colloids or in granular material, or even beyond physics, as I will show you in 15 minutes. Okay, so in the case of the glass transition, so there are many different approaches to try to understand the problem, and one of those approaches is based on the energy landscape. So first, if you want to think to a model for a liquid that forms a glass, you can take just n particle, very roughly speaking, which has an energy which is a function of all the particle position. So they have a certain interparticle potential. And so the number of particles goes from 1 to the n. And n, as you know, it can be very, very big. Let's say at the order of 10 to the 23. So what is the energy landscape? The energy landscape is just the function of all the position of the variable. And this makes the dimension of the problem. So since the configuration is in a number of dimension, which is, so the number of dimension is 3, because the dimension of the space, and n, which is the number of particles. So it's an extremely high-dimensional energy, extremely high-dimensional function. And now what has been studied and what has been, I would say, understood at different extent from theory, experiments, and simulation, and I can tell you more, is that this energy landscape is very rough and has very interesting properties. So in particular, if you look at the number of critical points, so which means that the number of points in which the gradient is 0, this at a certain value of the energy, this scale like exponential time, let's say, a function that I will call SE times n. So S is because it's like an entropy. It's not an entropy, but it's like an entropy. So what you see is that the number of critical points is really, really huge. I mean, remember, n is 10 to the 23, so this is something which is exponential to 10 to the 23. Okay, so it's gigantic. And so if you plot this function S of E, well, the typical behavior is the following. So here you will have, I mean, the lowest possible critical point in energy will be the ground state. And then you have a curve which goes like this. And it's actually something more that we know is that actually there is a certain energy that we call the threshold, such that there is what we call what has been called in recent years a topological transition. So what I mean is that here, if you pick a critical point at random at this energy, so this critical point is a saddle and has an extensive number of directions in which, well, the energy goes down. So let me write in a sketchy way. So here I will have the ground state here, and here I will have the threshold energy. And here, let's say you have many critical points, but which have many directions in which the energy goes up and many directions in which the energy goes down. And instead, if you are here, so here you have saddles. And here instead you have minima, local minima. Okay? So here in this regime, if you are below, while here you have actually a lot of local minima, and then the more you go down, well, the less local minima you have, and here you arrive here, in which you have just, well, a few of them. Okay? And the interesting thing is that this is really a transition, meaning that if you're above this energy, then, well, with probability 1, if you take one critical point at random, it would be a saddle, and here it would be a local minimum. It's just because, with probability 1, just because there are so many, there are exponential of n, that, well, typically you fall into saddle, and here you fall into minimum. Okay? And see, this comes from, let's say, solution of simplified models. And then there are simulation of realistic system in which you can try to see whether, of course, in simulation you cannot measure an exponential number of critical points, but you can try to see whether the things found in theory agree with the simulation. And then, well, the fact that there is a curve like this, you can also try to find from experiments. Okay? Again, it's an indirect way. Of course, you cannot measure the exponential number, I mean, the number of critical points in experiment, but you can try to given the entropy of the system and the entropy of the amorphous solid, you can try to compute this in an indirect way. So this was just to show you that, I mean, there are several indications that the energy landscape of liquids that form glasses is very complicated, is very rough. And one of the ideas is that the relaxation, the very slow relaxation that you find when you approach the glass transition is related to this landscape and to how the dynamics of the system explore this landscape. And one interesting question for physicists is that when you have a rough landscape in extremely high dimension, all the things you are used to understand of, let's say, stochastic dynamics in low dimension don't work anymore. At least you cannot, I mean, your intuition is not good. So we know that if you are in low dimension and we have some stochastic dynamics, we know that what happens, for example, if there is a barrier, we jump over a barrier at low temperature to go from one minimum to the other. Then, and in general, if you decrease the temperature, you get to a minimum. So here in this case, I mean, understanding, for example, jump across barrier is very, very difficult, and to some extent it's an open problem. In a case in which you have an exponential number of barriers and an exponential number actually of paths in which you can escape. Okay, so
is the threshold energy 10% more, a factor of 2 more than the ground state? It varies with material.
Okay, so let's see. So let's say it's a factor of well, okay. First, it's not that you really measure this energy smaller. You measure actually what you can see more is in temperature. So in temperature, maybe it's something that I can say. So if you are high temperature, the dynamics is fast. Then when you reach the temperature scale at which you are here, the dynamics really slow down a lot, and then maybe around here, the system falls out of equilibrium. So I think the difference in temperature between this and this should be maybe something like less than 1/3, roughly. Okay, so, okay, this was one example. And then there are other cases in physics in which rough energy landscape has been considered. So, for example, in case like protein folding or spin glasses. But I think it's here in the case of the glass transition that there have been more progress. And of course, I mean, this is just a way to look at the problem. At the end, what we want to understand is how really particle moves in 3 dimensions and why the dynamics slow down, well, maybe from the point of view of energy landscape, but also from the point of view of real space. And so all the approach has to be combined. So, okay, so this was, well, an example in physics. And now I would like to switch to another example, computer science. Another example of rough energy landscape, and something on which many people actually at the program have worked on, is optimization problem in computer science. So in the optimization problem in computer science, let's say in constraint satisfaction problem. So what you have, if you want to make an analogy, so here you have the variable are the position of the particle. Here what you have some variable that define your configuration. You have some set of constraints. And then you can define an energy function, which is just if you give me a configuration, so the energy function of this configuration is just the number of constraints which are not verified. Now, of course, since the number of variables is big, again, the energy is an energy of a very large number of variables. So, and here, well, if you have a configuration, so a solution will be a configuration of variables such that the energy is 0. And so you can ask questions like, how is the space of configuration? So all the manifold at energy 0, how is it? Well, especially if you vary the number of constraints with respect to the number of variables. And then also you can also study the energy, I mean, the configuration at positive energy. And again, something that I want to stress, and I will stress more, all these things, I mean, at the end, in general, what you want to know, I mean, you are interested in landscape because we think that they can tell us something about the dynamics in the system. So in this case, it's the dynamics of the physical system. Here in this case would be about the property of algorithm that you want to use to find solution. So to be concrete, actually, I would like to discuss the energy landscape of the case satisfiability problem, since many people in the audience in the problem work on this. So KSAT is one of the central problem in computer science. It's the first optimization problem that was shown to be NP complete. And well, one way to define it is that so if I define the variable, it's defined looking at Boolean variable, x1 to xn. So these are Boolean variables, and they can be true or false. Means that if you want 0, 1, or Eisenspin, plus or minus 1. And then you have a set of constraints. So they say, so the index of variable goes from 1 to n. And then let's say you have m1, m big N constraints. And so in these constraints are defined in this way. So let's say, for example, constraint m1 will be defined in this way. So I take one variable, let's say, I don't know, x2, for example, and I ask that x2 has to be true. So if I write this, it means that it has to be true. Or let's say x27 has to be false. So this means that it's false. Or, I don't know, x17 is true. Or I don't know, 45 is true. Okay? So this is a constraint. And then, I mean, the energy or a solution will be a set of variables such that m1 and m2 and m is true. So all the constraint has to be verified. Okay. All right. So, well, this is the problem. And so in optimization problem, there are two different ways of proceeding. So there is one case in which you look at the worst case scenario. So given all the possible instances that you can find, you want to know what's going to happen if you have the worst possible case, in which you want to know whether it's easy or complicated to get a solution, meaning whether it takes an exponential time in n or not. But then there have been a lot of studies in recent years, and particularly by physicists, on typical case. It means that you take an ensemble. Well, first, yeah, it's a different kind of question, and of course, depending on depending on the situation, there is one that can be more important or the other. I mean, I don't know, when you decide whether you take the bike or you take a car to come here, well, I don't know whether you think to the worst possible instance that can happen between your home or here, or whether you consider the typical instances. Okay? It depends really on what kind of question and what kind of problem you want to address. So what physicists and also computer science did is to study typical case, which means ensemble of instances. So for example, they consider what is called random k-sat. So in random k-sat, what you do, so let's say for k equal 4, so what you do is that you take one variable at random among the n, and let's say that I construct in this way. So the constraint mi, I take one variable at random among the n, so let's say x27, when I pick at random, I pick x27, and then they decide with probability 1/2 whether I decide that this is true or false. So let's say that I decide that is false. And then I do the same for the other one. So I pick another variable at random among the n. So let's say it comes x1, and then with probability 1/2, true or false, maybe false again, and so on and so forth. Okay? All right. Okay, so in this way, I create the big M constraint. And then what I ask is that when n go to infinity, and m go to infinity, so the number of variables go to infinity, the number of constraints go to infinity, in such a way that m divided by n has a finite value. Well, I want to know property of the system. Is the system easy to solve, meaning that I can solve it, for example, in polynomial time with certain algorithm? Is the space of configuration simple or very complicated? So this defines the problem. And so what has been found by actually more or less everybody's here from the physics paper. So it was a physics paper by, well, there were several papers, but I mean the one that from which I'm stealing the next figure that I'm trying to draw is from Marc Mézard, Lenka Steborova, Florent Zacala, Federico Reciter-Segni, Andrea Montanari, who was here, who will be here later, and Guillaume Semergien, who is the only one who is not at the program, but wanted to come and then had to teach. So, okay.
Can I ask for the M sub i's, how many variables do you allow to be engaged in that constraint?
Here, 4. Yeah. If k is equal to 4,
it's
just 4. Yeah.
Okay.
And yeah, I will describe k equal 4. So the space of configuration, so let's say a pictorial way to draw the space of configuration. Now I have this index alpha, and so, well, let's say that I draw the space of configuration with a square, which of course is not, because we are in extremely high dimension. Actually, the space of configuration is an hypercube in n dimension with n which go to infinity, but let's draw it in this way. And so when alpha is below a certain value that I will call, well, alpha d. So again, I'm cutting a long story short. In reality, there are much more, let's say, there is much more to say, and there are more phases, but I will not go through all the phases. So here you have the space of configuration, which is here, meaning that here you don't have configuration. Here you don't have solution. This is the space of solution. So the space of solution, when alpha is small, is simple. They are all connected one to the other, just doing small step. So changing a few variables, I can explore it easily, and they are all, well, it's simple in a way. So below a certain value, which I will call alpha d, so what you have is that it breaks in many different disconnected components. So here you have a solution, and here you don't. So it means that really, if you take one solution at random, well, one solution at random will belong to one cluster, and then if I take another solution at random, well, what happens is that the number of this cluster scale like exponential of a certain constant that actually I can call S again, times n. So this will be dependent on alpha. S alpha of n. So you have an exponential number of clusters, and then if you pick a configuration, it will belong to one of them. Cluster means that really configurations are organized in pockets, and the pockets are distant one from the other. And then, well, then there is a alpha C, at which actually this, you still have solution, but the number of clusters is not exponential in L. So let's say that you have just few of them. And then there is the alpha sat, which is when you don't have a solution anymore. So, well, this is nice. I mean, this was a very nice result that has been also proved in certain cases recently, in recent years. And the nice thing is that this, in a certain sense, is very similar, and this was, of course, known by the author of the work, to what you see here, except that in that case you have alpha as control parameter, and here you have the temperature. So here what you see is that below, well, actually here, above a certain energy, or let's say temperature, the landscape is very simple. It's very easy to move. Below a certain temperature here, it's very difficult actually to move. If you want to go from, let's say, what the system has to do, has to jump over barriers to go from one minimum to the other. The dynamics slow down in a repressive way. And then in this case, so if you arrive to the temperature at which the system becomes trapped in these states, in this case you have a thermodynamic phase transition, which would be the ideal gas transition. So we don't know whether this happens in a real system. We have no idea. But the nice thing is that the very similar energy landscape, you have it in that case. In that case, it happens. So in that case, indeed, here you have exactly the equivalent of the ideal gas transition. Okay, so this was to show you that, I mean, there is a lot of interesting information that one can get from the energy landscape. And this energy landscape, they have interesting properties in problems which are in very different fields. And the nice thing actually is that you can see also or hint that there is some kind of universality. It's not universality in the sense of universality class in second order phase transition, but you see that, I mean, you have some behavior here which is very, very similar to what you have there. So just to terminate, to finish the list of contexts in which you can find energy landscape, I would like just to tell you two more things, and then I will talk about questions. So there are two other cases that are very interesting for, and on which we are working in the program. Okay, so there is one case which is, okay, let me write rough, high, or let's say scale, well, rough, high dimensional landscape without a landscape. So I will explain what it is. So there are many interesting cases in which, let's say if you have glasses plus shear, or you have problem, for example, in recurrent neural network, or, for example, in ecology, so this is something on which some people, me included, work these days. So in which you have the dynamical equation that you have are typically, for example, gradient descent or Langevin dynamics, but the force does not derive from a potential. Okay, so the force does not derive from a potential. However, the model, you can change the model, and you can see what the energy landscape would be if you change the model in such a way that you get that the force derived from a potential. And so there are many cases in which what happens is that if you can change the model a little bit in such a way that the force derived from a potential, then you find exactly a very rough energy landscape. So what you can think is that in some of these cases, what you're doing is you have a system with a rough energy landscape, and you put on top of this non-conservative forces. And this gives rise actually to very interesting dynamical behavior. And this is something that is studied by people in the program. So this is one thing. And then the other thing that is that, so I discuss energy landscape in which, let's say, like the one of glasses, which is, so the quote-unquote is for my drawing, not for the glasses. So in which, I mean, okay, of course, this is very wrong because it's one-dimensional drawing of the energy landscape as a function of configuration. But the only thing that I want to show you is that this is what we the thing that I discussed before. There is one thing there is another ingredient which is interesting, which actually I think Mark Vezar called crystal hunting in a recent series of lectures that he gave, is that a case in which you have this kind of landscape and then you have a very particular configuration, okay, which has much lower energy. And now what you want to know in this case typically is, well, how low it is with respect to the other and whether you can find it dynamically. So, of course, there are cases which are, let's say in physics, you can think if you have glasses, I mean, in some cases for sure there is a crystal, and in some cases we are sure that actually the crystal is here, and I mean the glassy dynamics is here. Okay, what is interesting actually is not much the crystal for physicists. It's more interesting actually problem in computer science, like for example inference, in which actually what this is would be the signal that you want to recover. And this is the noise that you get just because you have noise in the data. And so the problem in that case, you have energy landscape in which you have, well, interesting competition between, well, the signal that you want to recover, so this minimum, and the randomness that can trap the dynamics. So this is another thing on which we work. Okay, so now I think it's enough for the context, and now I would like to tell you about what are the kind of questions actually that we address. And maybe, well, something that I want to convey really is that, well, in principle, we have different points of view because there are physicists, there are mathematicians, there are computer scientists. But, I mean, you have common questions and more or less common techniques to address them. Okay, so what are the questions that we are after for the many different problems that we consider? So, well, I think one question number one, which is rather natural, is can we characterize this landscape from a statistical point of view? So what I mean by this is, well, for example, what is the number of critical points as a function of the energy, for example, points. E exchange. So it really means that I take this landscape, I put a cut, and I want to know how many critical points do I have. Then I can ask, for example, are they saddle or minima? Are these, for example, this topological transition that I was discussing before? How are the barriers between critical points? All these things, in principle, well, can be asked and can be answered to some extent. Of course, this is really, I mean, you have to remember that the number of critical points scale like exponential of n, where n is the number of degrees of freedom. So this means that you have really new methods and you have to develop new ideas to treat this problem. And then, well, there is, I would say, the second thing, which is the most important, is certainly dynamics. In the sense that, as I said before, I mean, we want to understand landscape, but not, well, of course it's fun to understand landscape, but the idea is that we want to understand them in order to be able to say things about the physical dynamics, or the dynamics of algorithms, and in general the behavior of the problem. So the typical things that we want to know in the dynamics, so dynamics in rough high energy landscape is, so let's say there is one thing, which is 2.1, let's say, which is the behavior of physical dynamics. So for physical dynamics, I mean, for example, typically some kinds of Langevin dynamics or some, let's say, stochastic version of gradient descent. Well, why? Well, because this is the typical dynamics that you have if you have a system which is coupled to a thermal bath. And this is the case, well, in the majority of the physical system for which we are interested in and which have rough energy landscape. So, well, this is what we want to know as physicists, but actually is interesting also in the other things, like, for example, computer science. Because, well, in computer science, of course, you don't care about physical dynamics. You just want to find the best algorithm that give you the solution. At the same time, when you have very big data, at the end, you cannot, in many cases, use extremely smart algorithm. At the end, the things that you can do is you can do gradient descent or a stochastic version of gradient descent, and that's it. So for this, means that actually gradient descent is a very widespread algorithm in the case which you have a very huge number of data. So this means that actually, I mean, understanding physical dynamics is not just interesting to physicists, but is also interesting in the other fields. And then, well, as I said, well, of course, in computer science, you don't care about necessarily about physical dynamics. If you have a number of data such that you can use smart algorithms, then of course you want to use them. And so there is one idea is, well, what are the typical algorithms that you can find? What are the smartest ones that allow you a very good exploration of the energy landscape? And so, for example, in case in which you have a very rough landscape, can you beat them? Can you beat this landscape and find algorithms that bring you to the minima? And yeah, so it's a smart algorithm, or let's say smart dynamical exploration. So this is, of course, is very natural in the case of computer science. It's actually very natural also for physicists. So in physics, as you know, when you simulate, of course, this very smart algorithm will not describe the physics of the system. However, let's say that you are able to simulate in 1 second a glass that is formed after 1 million years. So, of course, then you start to think that you can start to answer very good questions in physics if you're able to do this. So finding extremely smart algorithms that allow you to get equilibrated system at very low temperature is something which is very important in physics. And so, of course, all these things indeed are interesting to physicists. And just to a small advertisement, this kind of algorithm were actually been found. And so we have algorithms that can give you super cool liquids which are equilibrated to extremely small temperature, actually temperature at which the experiment cannot reach. And well, in this case, there is, I think, only Patrick here as author of this paper. Okay, so, well, this is to give you the questions. And then to be concrete, I would like to go through an example, a simple model that has been interesting for many people in the audience. And so this just to show you how we address this problem. So let me first tell you what the problem is. So the problem is called Tensor Pca. So Pca stands for Principal Component Analysis. And so this problem of Tensor Pca is a problem that you can find actually in, for example, when you have signal processing, especially I think on movies, when you have images and for different frame of images as a function of time. Now, the model will be very simple. So you have, let's say that you have a tensor, T1, I2, IP. And in the ideal situation, this tensor is just formed by a vector, which is your signal, Vi1, Vi2, Vip, where Vi is just a vector, sum over I, Vi square, equal to n, and I goes from 1 to n. So this is the vector, is the signal. What is transmitted is this tensor, but then this is corrupted by noise. Okay, so here I add some noise, Gi1, IP, and here I put a lambda, which is the signal-to-noise ratio. And so this is what you get, and this is what you would like to recover. And then, well, if you have this, so one possible way to do is, if you have this tensor, is to, so there are different ways. So one way would be you do the minimum over all configuration Si, such that sum over Si square is equal to n, of, well, T I1 IP minus Si1 SIP square. Okay? So this means that, well, in the ideal world, this Ti1 IP is just the vector here that you have. So you take, well, the difference between this, and then you take the square, and then you try to minimize this. Okay? Is the problem clear? All right. Okay, so now if you look at this problem, now you take the square. When you take the square, you see that when I square this, so the square of this does not depend on S, so it's not important for the minimization problem. When I take the square of this, well, if I sum over I, since sum over I Si square is equal to n, so this gives me just a constant, so the square of this is not important for the minimization. So the only thing which is important is the cross product. And when I do the cross product, then I get minus 2. Sorry, nobody told me, so that's a bad sign. So there was a sum here, I1, IP. So I have to sum over all the components. Okay. Okay, this is the scary moment when you teach and you.
It's Einstein's notation. It was implicit.
Yes, thank you. Okay, so when you take. Huh?
There might be a lambda in there.
Yeah, I should put a lambda. So maybe the lambda I will put it here. Okay, wow. Okay, let me put here the lambda. This will be probably a big mistake for what follows, given that the lambda was somewhere else. Okay, the lambda will float in the field. Okay, so when I take this here, the cross product, I will have sum over, so I take, will be the minimum over S of minus 2, sum over I1 IP of T I1 IP times S. So in T I1 IP, I have two terms. I have first this term here, which gives me a lambda here, and then I have G I1 IP, S I1, S IP. And then I have the other term, which is minus sum over I1. So I would have I1 IP, VI1, VI2, VIP, SI1, SIP. So this gives me sum over VI, SI to the P. And then I guess there is a factor of 2 in front. Okay? I hope that is roughly correct. Okay, so now I can redefine all the, so now the J here, this was noise. So it is represented like Gaussian random variables, independent, IID. And so, well, if I redefine all the, let's say, the variance of the J, which has average mean 0 and certain variance, and I remultiply this, I can, I can write this as an energy function, E of S, where I have a first term here, so let me change the J. I will call J minus J. I will call, let's say, well, actually, J, we'll call it minus 2 lambda J, we'll call it J, okay? In any case, J is an even random is a Gaussian variable, so I can always redefine it, putting A minus inside. And then I multiply everything in such a way that my lambda now is here, because I like the lambda here. And so what I get is sum over I1 IP, JI1 IP, SI1 SIP, and then I have minus lambda, sum over I, VI, SI to the power P. And then if I want to have good scalings when n go to infinity, and this you have to trust me, but it's easy to see. So I should put an n in front here, and then I should say that GI1 IP squared, so the variance is equal to, let's say, 1 over n to the p minus 1. Okay? So in this way, I know that these two terms are of the same order. They're really competing one against each other. And now if you look at this problem, so this problem that it's a problem which doesn't come from physics, actually the interesting thing is that this part here, so this term, so terms number 1, is one of, well, the first studied mean field spin glasses. Generalized, actually, mean field spin glasses. And for this, actually, we know really a lot. So first, its energy landscape is exactly of the form that I give at the beginning. So actually this, even though this has nothing to do, of course, with a super cool liquid, actually the statistical property of the energy landscape of this problem are really the same of the one that we know that super cool liquids that form glasses display. So actually this system, in a very crude way, is actually a mean field model of, let's say, of the glass transition. Not the spin glass, but the glass transition. So all the property of the energy landscapes are the one that I described before. And here, so what you have is that on top of, let's say, the rough energy landscape, you have this term, and this term is the signal. So it's just a very low energy minimum that I was discussing before. So, well, in this case, well, the questions that one can ask, and that were asked, are exactly what I wrote here. So what is the energy landscape? Can we study the energy landscape in a very detailed way? And how this energy landscape influences the behavior of algorithms? Okay, so the question number 1, which is, what is the behavior of the energy landscape that we can study? So this, well, it has been also, I mean, has been studied by physicists, but also to a large extent proved rigorously by mathematicians that are here at the program. So let me show you what happens when I increase lambda. So lambda is our control parameter, is the signal to noise ratio. And I will again just draw a picture, which just to be simple. So this is the, let's say, the hypersphere in n dimension, which is here is just a circle. And so let's say that here there is the vector v, which is the signal. And then I can ask, depending on lambda, how is the energy landscape? So of course, if lambda is very, very large, I expect that the energy landscape will have a global minimum in the direction of the signal. If lambda is not too large, this will not be the case. And can I have many, many multiple local minima, for example, that can trap the system? So what is found is that, so in this case, so there is what we call the equator here, which are all the vectors which are orthogonal to this one. And here you have really a lot, so the majority of critical points are here when lambda is small. Lambda. So here you have the majority of critical points. So you have for lambda small, below a certain value that I will call lambda 1, the number of critical points, actually let's say the number of even local minima, is exponential in n, and is located here in the equator, which means it's orthogonal to the signal. And the other interesting thing is that here you are in extremely high dimension, so the majority of the configuration are just here. It's just that there are so many that in high dimension, if you take a vector and then you take so you take a vector here and then I take a vector at random on the sphere, when you are in very high dimension, with very high probability you are orthogonal to it, just because of entropy. So the majority of the configuration, which means an exponential number of configuration, are here. And here you also have an exponential number of local minima. And then, well, what happens here, you have the signal, but if lambda is not big, actually, from the point of view of the energy landscape, let's say that you don't see it. So if lambda is small, there is no, the minimum is not popping out. And then, well, there is a certain value of lambda at which I can say, so you still have here, you still here have an exponential number. So actually I can draw it maybe like this. So you have an exponential number of local minima here. You still also have an exponential number of local minima if you go a certain latitude here, which is at a finite distance. So it means there's a finite projection on V. And then, so if you are in this lambda 1, so what happens here is that this decreases. And then there is one local minimum that pops out, which is here, okay? It's not in the direction of the signal, but again, it's not orthogonal now. And so in this regime, so one way to think about is that, so you have this minimum, which is special, which is not the global minimum, that appear in the landscape, okay, which is this one. Okay? And then, well, if you increase more lambda, so be above a certain lambda 2, so here you have, it becomes the global minimum, so this becomes even smaller. And this is more in the direction of V. So this, and now the energy landscape is like this, let's say. And then you have really the minimum here, which is the global minimum. And then there is actually, let's say, a certain lambda 3, at which, while here you have that the blue and the white are almost aligned along each other. And here what you have is that the number, so this number of local minima is very, very small here. And actually can become less than 1 over square root of n. So it means that, 1 over square root of n is the typical, so if I take a vector at random, is typically have a scalar product which is of order 1 over square root of n with, well, if this is normalized to 1, it's of order 1 over square root of n with this one. So a typical, if you are above lambda 3, a typical vector that you take at random will be here. So it will not be in the band which correspond to the local minima. Okay? So starting from this, you can start to think what's going to happen to algorithm. So the first thing is what's going to happen if I do gradient descent. Okay, so a good time to take guesses. So what do you think? I mean, not for the people from the program, of course, but for the other from the other program or other people. So what's going to happen if I do gradient? I start from a random initial condition and I do gradient descent. What's going to happen? When gradient descent is going to be able to recover the signal? Lambda, so okay, of course, not before lambda 1 for sure. But so there are three possibilities: is lambda 1, lambda 2, or lambda 3 that are the which is the threshold, the algorithmic threshold for gradient descent, the algorithmic threshold for gradient descent. When is going to happen? Okay, I don't no vote.
I didn't see the physical distinction between what's between lambda 1 and lambda 2 and lambda 2 and lambda 3.
So in lambda 1,
No, the second and the third bubble.
the second and the third. So in the second,
I don't see the physical distinction.
okay. So in the second, it exists a local minimum, which is, let's say, is not exactly in the direction of the signal, but with a good overlap. But it's a local minimum. It's not the global minimum.
Okay.
And here it becomes a global minimum. Okay. So well, I will tell you the answer, and we don't do.
Take a vote.
We take a vote. Okay. So how many people say lambda 2? Raise your hands. 2, 3. Okay. Lambda 3. Okay, the majority is for lambda 3. There was not a quorum, however. So, okay, so indeed, I mean, lambda, so it's, what happened here is that, of course, well, before lambda 1, you cannot retrieve the signal. It's not even a local minimum. Between lambda 1 and lambda 2, well, gradient descent, I mean, in general, you cannot recover, actually, the signal because, yes, it's a local minimum among many, many others, so there is no way in which you can find it. Now, between lambda 2 and lambda 3, well, this is the global minimum of the energy, so maybe gradient descent or some stochastic version of gradient descent could make it. The problem is that when you take a configuration at random, it will be typically here, and it will be in a region of the landscape which is very rough, with an exponential number of minima in which can be trapped. And so what we know is that here, gradient descent or stochastic version of gradient descent will be trapped. So you don't find the signal. Okay, so for example, if you use Langevin dynamics, here the time it takes actually to find the global minimum is exponential in n. And if you do the gradient descent, well, you are doomed, you don't go there. And now here, if you are lambda larger than lambda 3, so then gradient descent makes it. In a certain sense, it's easy because if you take a configuration at random, you are out of the region, which is very complicated. And then you feel the gradient because this is a very strong global minimum, and then you go there. So that's, well, this is typical questions that one can ask. And then, well, let's say question, so this was, let's say, question 2.1 is gradient descent and Langevin. And then you can ask the other questions that I said. Question 2.2 is, well, what about if I do smart algorithm? So actually, maybe I can say lambda 3, which is here in my units, there scale like n p minus 2 divided by 2. Now, if you use smart algorithms, which are not physical in a sense, they don't use the gradient descent, then actually you can put this. You can find that you have a certain lambda critical, which goes like n to the p minus 2 divided by 4. Okay? I will not go into describe the algorithm. You can tell you later if you want. Just to tell you there are smart algorithms which are not related to simpler exploration of the landscape that can actually beat gradient descent. And then the question, of course, is, okay, can one do better? Or is it just impossible? So there is a hard phase, meaning that no matter what you do, I mean, if lambda is less than lambda c, you will not be able to recover the signal in a time which is not exponential in n. So this is the typical question that we ask. And so what I can tell you is something that we did. For example, when p is odd, we found, actually here, together with Federico Richtersen and Chiara Camarota, that actually we can beat this using a generalized version of gradient descent and have a lambda which scale like square root of log n. I mean, if you, again, square root of log n is not bad. Huh?
For p equal 3.
Yeah, for p equal 3. Yes, right, Federico. Yeah, for p equal 3, is lambda goes like square root of log n that you can compare here to something which instead is a power law in n. Of course, I mean, square root of log n is something which is, to all practical purposes, is of order 1. Okay, so this is just to give you was just to give you an example of the kind of questions and problems that we look at. And I would like to conclude talking about problems in machine learning, on which we really work a lot in the last 3 weeks. And it makes a nice connection with the other program. Okay. So we introduce, the problem in machine learning. Of course, everybody knows it here, almost in the audience. So why rough energy landscape can be interesting, or maybe high dimensional energy landscape, whether rough or not, we don't know, in the problem of machine learning. So what we discuss a lot, actually, in the last 3 weeks, is the problem of supervised learning. And several, let's say, mean field limits of it. So in this, the problem of supervised learning, you typically have a set of data, which I will call xi. Let's say images, for example, of cat and dogs. And you want to classify them. So you want to find a machine that is able, if I give that is able to classify these images. And a machine, what it means is just to find a function with certain parameter, w, that I'm going to fix in some way, in such a way that, if x, let's say, is a cat, it's going to be positive, and if it's a dog, it's going to be negative. Okay, so in this way, if I just give an image, I look if it's positive or negative, I can classify it. Okay, and how these functions are constructed, so it's a simple way to construct them, which is, for example, fully connected neural networks. So you have, let's say that here you have, this is a notation for all the component of the vector x, which correspond to the image. So this will be the image x, the vector of image x. And then so you have weights here, so which enter into a node. So this means that I do the scalar product of x with the weight that enter into this node. Let's call this node, I don't know, a node number 10. And then, I do the same for many other nodes here. So I have many other set of weights. Okay. And then each one of these input in the node and then is transformed by a nonlinear function. Let's call it sigma, which let's say is the same for all the nodes. And then each node spits out an output. And then I can continue. With this output, I do exactly the same construction. I multiply by other weights that enter in other nodes, and so on and so forth. Okay. And so at the end, what I get is this function. I created this function, which is f of x w. All the w are constructed in this way. The nonlinear function can be different. And I want to actually find the w in such a way that the machine is able to classify the data. So one way to find the w is to minimize, with respect to w, what is called the train loss. And here, just to be simple, it's a sum over mu from 1 to m of, again, something which is not done in practice, but just to be simple, this will be y of mu minus f of x mu. W squared. So y mu will be, let's say, +1 if it's a cat, and -1 if it's a dog. And so I want to find the parameter in such a way that this is minimized. Okay, so now, what this is a problem of, which is, at least in which you have a high dimensional energy function or landscape that appears, the number of w's can be actually very, very big, very big. So the number of w's that you can find in application can be, for example, 10 to the 8 or even more. And the number of data, just to give you some order of magnitude, can be, for example, 10 to the 7 or more. So the interesting thing is that the number of w is really huge. So it means that now if I want to minimize this, so this is just, if I sum over data, it's just a function of w. So this function of w is, again, the function in an extremely high number of dimensions. And what you want to do in practice is that when you train the system, you want to minimize this function. And also the questions that one can ask and have been asked and that we addressed at the conference and during the program. So question number 1, so this is called, let's say, training loss. So how is the landscape of the training loss? The training loss. So in particular, is it rough? Is it, let's say, roughly convex, meaning that it's not convex, but you don't have serious barrier? And how this actually depends on the number of W's and the number of data. So what it seems is that when the number of W's is actually much larger than the number of data, which is the case that is considered in practice in over-parameterized network, this landscape is not. I mean, it's maybe is not is not convex, but it's not very complicated. It's not full of barriers like the one of glasses that I discussed before. And then question number 2 is, I mean, how the training dynamics proceed in this landscape. So, well, first, is it glasses in some sense? I mean, how just the system goes down and explore this landscape? I mean, the exploration in general is done by stochastic gradient descent, which, well, it's a stochastic version of gradient descent for people that don't know what it is. And for people that know, well, they know that I'm a little bit imprecise. And, okay, all right, so this is another question, really, the dynamic, how the training dynamic proceeds. And then there is a third question, which is something new with respect to what I discussed so far, which is how good. So, well, let's say the answer to this is that in many cases, when the system is over-parameterized, when the number of W is much larger than the number of data, you find, so the system is able to find the global minimum or almost the global minimum. So you go down to a training loss, which is roughly 0, okay, which is the best possible thing that you can do. So clearly, from this point of view, the system is not so glassy. I mean, in a glassy system, you don't go, in general, very close to the minimum. So it depends then of the glassy system, but here, when you don't go, here you don't, especially you don't need an extremely large time compared to the number of variables, which is 10 to the 8th. Okay, so the other question is so let's say, or maybe, voila. Or, well, let's say it this way. So why actually the minimum that you find generalize well? So what I mean by this, what I mean is that here you have a set of data that you use to train the system. But then you provide to the system new data. And you want actually that the system, yeah, of course, you want it that is, well, you expect that it's good on the training data because you trained on it. But what you want is that it's good on the data that they didn't see, the new data. So in a certain sense, well, this is the training loss, this is the landscape that you use to minimize, to train the system. But actually what you want to do is that the system is minimize the test loss, so something that the system didn't see. And so, well, this is another question. And I mean, maybe I can tell you what the idea that, I mean, we have and the community have and that appear, yeah, I have to stop. I'm finished. So the idea, which are really related, I think, in which I think the dynamics in energy landscape plays an important role. One is that probably the initial condition actually matter a lot. So what we know is that over-parameterized network go to a training loss which is almost 0 and generalize well. Why is it? Well, maybe, I mean, it's not true that whatever are the initial condition is going to happen. And maybe part of the answer relies on the property of the initial condition. Then part of the answer relies on the dynamics that you use, so the algorithm, which is stochastic gradient descent. And part of the answer is on the special kind of landscape that are involved. And this is probably meaning that given the set of data that we have, and given this architecture that we have, we don't have any possible landscape, but we have some very special. We have some special landscape in which actually in which is possible to find by over-parameterization minima that generalize well. So these are things on which we're working, and again, which we worked on in the last week. and which we think the idea that we have, which comes from the study of high-dimensional landscape, can be useful, and maybe we can interact a lot with the other program. So thank you.
I was wondering how much the mathematical techniques you use rely on the thermodynamic limits, and whether they break if you're using finite systems, and if we know for as long as we're good, and these sort of questions.
Okay, so well, first they rely a lot on some kind of scaling limit, in the sense that you have to, I mean, in the case of physics, yes, you have to in general take the thermodynamic limit, and then you can try to discuss asymptotic correction. So that's one way to proceed. I mean, when you start to work at, let's say, finite number of variables, then it's very difficult to get, let's say, generic answer. So you can get generic answer if you say, okay, n is large but not too large. N is large but it's just it's just a correction of the thermodynamic limit. Or in other case, you can try to work, I don't know, if you think that the ratio of two variables is important, you take a limit in which both variables go to infinity, like I discussed for case satisfiability, but with the ratio which is fixed. But in general, well, if n is really, the number of variables is really finite, it's very difficult to give general answer. But, well, in a sense, if you take, I don't know, four molecules together, there is no liquid, no crystal, no phases. I mean, you need some kind of large number to give some kind of general answer. So, but the answer is, either thermodynamic limit or asymptotic correction. This is in general what we can do. And if there are people that disagree in the audience, in the program, say it.
So you discussed these two transitions where you have a transition, so in the first part of your talk, where you have a transition from having mostly saddles, or let's say only saddles, to having only minima. I was wondering if there's any finer statements about this regarding sort of what the nature of the minima are. For example, what's the distribution of the eigenvalues of the Hessian?
Yes. So yes, we know actually a lot. So I will tell you a little bit, and then offline we can discuss more.
You can just say yes.
Okay, I see.
Just say yes and point to the person I'm supposed to ask this question to later.
Okay, man. Yeah. Okay. You can ask. Yes. We know a lot about the distribution of eigenvalues of the Hessian.
Okay.
Yeah.
Cool.
Yeah, please.
So when you were describing gradient descent on this example, you were thinking of random initialization?
The random initialization, yes. Configuration of random, yeah.
So are you working on some smart algorithm also in the context of machine learning, like to reduce this threshold?
There are, yes, there are people working on this. Yeah.
Yeah, what's a smart algorithm?
So it just, let's say, for example, can be an algorithm that uses non-local moves. That
swap kinds of things.
For example, it's in the context of physics, for example, yes, the smart algorithm that has been found to accelerate the dynamics of supercooled liquids are cases in which you swap particles that can be, or not far away, but you do swap that the normal dynamics will be never able to do on, let's say, realistic time scale. Then, in computer science, they are much more smart, actually. It's not so smart, after all. It works well, but it's not so smart. And Patrick is not hearing me because he's discussing.
I was wondering, are the algorithms being developed kind of programmatically, or is it more like a constellation of different ideas people have, or they're kind of like a landscape of algorithms people are trying to?
Okay, I can answer for physics. I think I'm not, maybe somebody else can answer. I think in computer science there is much more work. In physics, I think it's more, I would say, well, for second order phase transition, of course, there have been really a program done based on the understanding of collective phenomena close to the second order phase transition. But for this rough energy landscape, it has been more, I think, trial and error. Well, I disagree, but I think it's more, for physics, not for computer science. for physics, okay, that's my opinion. And I see that Lenka disagrees.
All right, thank you.